Hello everyone, I'm Connor, and I'm going to be discussing the solution for the USACO December 2022 Silver Contest Problem 2, Circular Barn. In this problem, Farmer John and Farmer Naj are playing a game where they are in a circular barn with some number of rooms, and each room has some number of cows in it. During a move, Farmer John goes first and then Farmer Naj goes, and during a move, they can remove either one or a prime number of cows from the room. And then Farmer John goes first and Farmer Naj goes next, and then they move on to the next room in the barn. And this game continues until one of them cannot make a move because there are no cows left in a room. So this is a type of game theory problem. In game theory, we want to figure out who wins a game or who loses, and typically there's an optimal strategy to be found. Take this barn here for example. In this barn, the first room has 4 cows, the second room has 9 cows, and the third room has 17 cows. Farmer John and Farmer Nodge start in the first room. Farmer John can take out any number of cows from this room, from that's a 1 or a prime number. Since there's only 4 cows, that means he can take out 1, 2, or 3 cows. And no matter what Farmer John chooses, if he chooses 1 cow, then there will be 3 left, so Farmer Nodge has the option to take out 3 cows from the barn. Similarly, if Farmer John takes out 2 cows, then Farmer Nodge can take out 2 cows as well, leaving Farmer John with none left. And no matter what Farmer John chooses, Farmer Nodge will be able to reduce the number of cows in the room to 0. This isn't an issue immediately, since John doesn't have to take a move until he circles back around. But if none of the other rooms have an immediate victory for Farmer John, then he's going to lose when he gets back to the first room again. So, since this room is solved, they go to the next room. This room has 9 cows. Once again, there's no immediate victory for Farmer John, since he cannot remove 9 cows straight away. But he is able to remove 3 cows, leaving Farmer Nodge with 6, and then Farmer Nodge can remove however many cows he wants, but he won't be able to empty the room. Finally, they get to the last room, room 17, and in this room, Farmer John is able to immediately remove all the cows since 17 is a prime number. So Farmer Nodge is left with no cows left, so Farmer Nodge loses and Farmer John wins. So this case, Farmer John wins. And in game theory games, you typically assume both players are playing optimally. So there's a way to determine the victory for the problem, and someone's always going to have a winning strategy, whether that be Farmer John or Farmer Nodge. So how on earth do we solve this problem? Right now it's pretty complicated since there's so many rooms and we don't know what anyone wants to do in any room at all. So let's simplify the problem a little bit and start with one room. So let's say we have a room, one room, with X cows. And we want to figure out who wins if we just have this single room. And since this is a single room, when they loot the room, they immediately come back around to it. So that means that it's basically just they make the moves over and over again without any other rooms in between. So let's just try some small amounts of cows. Let's say they have 1 cow. And then since Farmer John goes first, he can just immediately remove this cow, and then Farmer Nodge will have nothing left, so Farmer John wins. I'm gonna write his name as FJ. Let's say you have 2 cows. If you have 2 cows, same thing happens. Farmer John just removes both of them. And then he wins. How about 3 cows? Well, same thing. 4 cows is a little more interesting though. Since Farmer John can't immediately remove 4 cows, he only has the options to remove 1, 2, or 3 cows. If he removes 1 cow, then they are left with 3 left. If he removes 2, then there's 2 left. And if they remove 1, there's 1 left. And in any of these cases, then Farmer Notch will be able to remove the rest of the cows. So that means that when Farmer John plays again, he doesn't have any cows to choose from, so he immediately loses. So Farmer Nodge wins, who I'll write as FN. So let's move on to 5. 5 is pretty simple again. It's a prime number, so Farmer John can just remove it and win. Farmer or 6 cows is also pretty interesting. This is another number that Farmer John is unable to remove. So he can remove 1, 2, 3, or 5 cows. And this leaves him with a total of 5, 4, 3, or 1 cow left in the room. If he removes 5, then Nodge will be able to remove all 5 of them. So in this case, Farmer Nodge wins. So Farmer John probably doesn't want to remove 1 cow. If he removes 3 cows, then 3 cows are left, and once again, Farmer Nodge wins. And same thing for 5 cows, leaving them one cow, and Farmer Nodge wins. However, the 4 cow case is a bit more interesting, since this essentially just loops back to this case. So, however, it's in the other order. Since Farmer Nodge is going first instead of Farmer John, then Farmer John has a winning strategy here, because Farmer Nodge can't choose any amount of cows without Farmer John being able to remove all of them all next. And then Farmer John will just win. So in this case, Farmer John does have a winning strategy if he just removes 2 cows, which puts Farmer Nodge at 4, so Farmer Nodge cannot win. Now let's do 7. 7 is an instant win for Farmer John again, since it's a prime number. And 8 is not an instant win, so there are several ways to do this one. You can remove 1, 2, 3, 5, or 7 cows. So if he removes 1, then there's 7. 2 is 6. 3 is 5. 5 is 3. And 7 is 1. And we can immediately rule out the ones that result in a prime number, since that means Farmer Nodge will just instantly win. So we're left with 7, 5, 3, and 1. So this leaves 6 cows for Farmer Nodge. But this once again loops back to this case. And since that case was a win for Farmer John when Farmer John went first, this means that if Farmer Nodge goes first, this will be a win for Farmer Nodge. If you wanted to, you could show all the possibilities for it, and see that Farmer Nodge will want to choose to remove 2 cows to go down to 4, and then we're back at this case up here. So in this case, it's Farmer Nodge that wins. So with this set of cow counts done, we can kind of see a pattern here. We see that for 1, 2, and 3, 5, 6, and 7, Farmer John wins, but for the multiples of 4, Farmer Nodge wins. And if we think about this some more, this kind of makes sense, and it would generalize to other cases. Let's see why. Let's assume the current room, the single room, has x cows, where x is a multiple of 4. So since x is a multiple of 4, then we can make a few observations based off of this. First of all, and let's assume that Farmer John goes first. First of all, if Farmer John has a multiple of 4, then it's impossible for him to get to another multiple of 4. And this is because the difference between 2 multiples of 4 is also a multiple of 4, which is not a prime number. So that means that it's impossible to pick that many cows. So another observation we can make is that Farmer John will always never be able to win if he has a multiple of 4. This is because if he wants to win, then he would need to remove all the cows in the pile. But since x is a multiple of 4, it is not a prime number, so he cannot win. Also, since 0 is a multiple of 4, that means that he can lose, since having 0 cows means you lose. So let me write that down. Okay, and the final observation here is that no matter what Farmer John chooses, Farmer Nodge always has the option to get him back to a multiple of 4. And this is because Farmer John can only choose like prime numbers and 1. And this means that he'll always go to something that isn't multiple of 4. But Farmer Nodge has the ability to choose 1, 2, and 3, and one of these options will always get him back to multiple of 4. Because whatever Farmer John chooses will either end up at a multiple of 4 plus 1, a multiple of 4 plus 2, or a multiple of 4 plus 3. And then Farmer Knowledge can just choose whatever it takes to get down to that multiple of 4. So let me write that down. And if we look at all of these observations together, it seems like Farmer John can never win if he has a multiple of 4. So I'm going to write that. So having a multiple of 4 means you lose. And note that I didn't just write Farmer John, because if Farmer Nodge ever gets to a multiple of 4, then he also loses for the exact same reason. Because he can't get anywhere other than, he can't get to another multiple of 4, so he cannot win. And then Farmer John can just set Farmer Nodge back to a multiple of 4. So essentially, if you ever get a multiple of 4, then you're basically stuck, and you can't possibly win. This also gives us a hint of a winning strategy for this. No matter what Farmer John does, or Farmer John will always want to choose something that'll get Farmer Nodge down to a multiple of 4. We know that he'll always have the ability to do this, and if Farmer Nodge has a multiple of 4, then he cannot possibly win if both players are playing optimally. So Farmer John's winning strategy is to get Farmer Nodge down to a multiple of 4, and Farmer Nodge's only chance of winning is if he starts at a multiple of 4. Is if Farmer John starts at a multiple of 4. So now that we have an idea of the general strategy for a single room game, let's generalize it to multiple rooms. Notice that if we have n rooms, then that's essentially us playing n games of this at once. However, if one room ever loses or wins, then that means that the game is instantly over. So essentially, their answer is just whichever room loses or wins first. This means that the speed in which a player loses or wins actually matters a lot, because if someone is forced to lose, they want to probably prolong that loss as long as possible, just so that they have a chance to win in one of the other rooms earlier. So since how long it takes is important for a room to end, we want to figure out what's the best strategy for each player, so that they either win as fast as possible or lose as slow as possible. It turns out there's actually only 4 cases that we have to consider. We can consider when it's a multiple of 4 plus 1, multiple of 4 plus 2, multiple of 4 plus 3, or just a multiple of 4. And all of these cases kind of just turn into each other, because you can always convert anything that's not a multiple of 4 into a multiple of 4, and you can turn anything that is a multiple of 4 into a non-multiple of 4. So let's start with the case where it's a multiple of 4 plus 1. So I'm going to write multiple of 4 plus 1. And this will be case 1. So in this case, Farmer John, well, we're going to assume that all of these cases are what Farmer John's dealing with. So Farmer John has a multiple of 4 plus 1. And since Farmer John wants to win as fast as possible, since we determined that these cases are winning for Farmer John, that means he wants to get the number as low as possible, because Farmer Nodge is going to try and delay as much as possible, and the higher number it is, the more that Farmer Nodge can delay by just picking small numbers of cows. So we want Farmer John to be able to choose as large as number as possible. However, we also need to make sure that Farmer Nodge still gets a multiple of 4, because that's the only way that Farmer John stays winning, is if he forces Farmer Nodge to have a losing multiple of 4. So, and the way we do this is we find the largest prime. We find the largest prime that has is also a multiple of 4 plus 1. And when we subtract this prime from our original number, then we're always going to get a multiple of 4. And since it's the largest prime, that means that Farmer John gets down to a low number as fast as possible. So that's the case for multiple 4 plus 1. Let's do case 2, where we have multiple 4 plus 3. I'm just kind of doing this in a random order. So in case 2 turns out to be very similar to case 1, because it's winning for Farmer John, so he has to find the largest prime that is also multiple of 4, this time plus 3. So you can write the same, but plus 3. again. So now we have our slightly more complicated cases. Well, I guess this one isn't too bad. But case 3 is multiple of 4 plus 2. So in this case, Farmer John still needs to force Farmer Notch to get a multiple of 4, but this time there's only one way for Farmer John to be able to do that, and that's when he's subtracting two cows. Because any other number will not put Farmer Notch at a multiple of 4. And so the only way to do this is Farmer John chooses 2. So yeah, he can't choose like 6 or 10 or something because none of those are valid primes. So now we have one last case, which is case 4. And this is just a multiple of 4. And this is special because this is our only case where Farmer John is losing. So we want Farmer John to lose as slowly as possible. So how do we do this? Well, we know from our uh, earlier observations that Farmer John cannot get to another multiple of 4. So that means that Farmer John can only force Farmer Nodge into one of these 3 cases. So Farmer John wants to force Farmer Nodge into the case that takes the longest for him to lose. So that is equivalent to the case that takes longest for Farmer Nodge to win. And looking at these 3 cases, this one might go straight down to 0 if the number is a prime number. This one could potentially also go straight down to 0, or at least a very low multiple of 4. And this one, however, only goes down one multiple of 4 at a time. Because in the case where Farmer John has something like 60, then if he chooses 2 to go down to this case, then Farmer Nodge has to choose 2 as well. So it goes down from 60 to 58 to 56, and then it just keeps going down by 2 every time. So that's the slowest way that Farmer John can lose. So in this case, Farmer John also chooses 2. And to go to case 3. So those are our 4 cases. So now we need to figure out exactly how long they take, because whichever room wins or loses first, then that room will be whichever room determines the answer. So I want to figure out how long they actually take, and we're going to do this in terms of how many rounds it takes. Let's start by calculating this for case 3, since it's a very simple case. In this case, every time Farmer John chooses 2, and then we go to case 4, and at case 4, Farmer Nodge will always want to choose 2. So then we go back to case 3. So it gets stuck in a loop where Farmer John chooses 2, then Farmer Nodge chooses 2. So that means if we start with x cows, then it takes x over 4 rounds if we floor it. So this is the case because every round it goes down by 4, since there are 2 turns for each person, or 2 turns in total per round. So it goes down by 4 per round. So it takes x over 4 rounds for it to get down to 0. Same thing actually happens for case 4. This is also x over 4 rounds. And it's actually a floor x over 4 rounds, but I guess it doesn't matter in this case since x is a multiple of 4. So this also takes floor x over 4 rounds because Farmer John chooses 2, then Farmer Nodge chooses 2, etc. So it's basically the same thing, except this time we know Farmer John loses. So let me write that. Now we can look at the other 2 cases. So in these other 2 cases, we have that Farmer John will always want to choose the largest prime that is also a multiple of 4 plus 1, or plus 3. And after that prime, then that means it'll be converted into case 4 for Farmer Notch. So let's say that prime is p. The largest prime is p. Then after the first move, the number of cows will get reduced to x minus p. So after that, then there'll be some number of rounds remaining. Since we're now at case 4, then it happens the same way. So it takes chooses 2, then chooses 2, then chooses 2. So it goes down by 4 per round again. So the total number of rounds is, after this first one is chosen, then we essentially go back into the case 3, case 4 loop. So we're given a total number of x over p over 4 rounds, x minus p over 4 rounds. And that applies to both of these cases. So now we know the amount of rounds that each takes to win. So now that we have all the calculations for the cases done, we want to just figure out which room will lose first. So if we're given a list of rooms like 12, 18, 16, 22, 19, etc., we want to loop through all the rooms. So start with the first room and calculate how many rounds it takes for it to lose or for it to win. So in the 12 case, this is a multiple of 4. So if you take floor of 12 over 4 rounds, this will take three rounds to lose. Similarly, we look here for 18. This is like case 3. So in this case, it'll also take x over 4, which is 4 to win. And we keep calculating this for all of the different rooms, and we see which one will lose first. And we can calculate this by just looking at which of these has the lowest number, and in case of the tie, looking at which one comes first in the room list. And we want to keep track separately of losing or winning, because if a room loses before a room wins, then that means it's an overall loss for Farmer John. And if a room wins before a room loses, then it's a win for Farmer John. So yeah, that's the general idea of our solution. And there are some details, like actually finding this largest prime. There are a couple ways to do. So you could either loop through all the primes, which essentially implies that you would start at the current prime x, or the current number x, and then you go down by multiple of 4 until you find one that is a prime. And that would make sure that you get a prime that has the same multiple of 4 plus n. So that's one way. Or you could do a pre-calculation, where essentially you go through every single number. So let me draw this. So you can essentially go through every number and figure out what's the greatest prime that's less than or equal to this number with the same mod plus 1 or mod plus 3. And so let's calculate that now. So in this case, 1 we consider to be a prime, even though it's technically not. But in this case, the lowest prime that's plus 1 under 1 would be 1. And the lowest for plus 3 doesn't exist because we haven't gotten there yet, so we just say 0. Or like null or something. And then for 2, the lowest prime that's equal to a multiple of 4 plus 1 below 2 is still 1. So we just copy that over, and that's still empty. Over here, this is still 1, since the lowest prime that's a multiple of 4 plus 1 below 3 is still 1. However, for this, now we can set this to 3, because the lowest number that's a multiple of 4 plus 3 below 3 is 3. And then we can continue along like that. For 4, it's 1 and 3. For 5, now 5 is the new highest prime number below 5. That's a multiple of 4 plus 1. And we just continue along with 3. For 6, it's still 5 and 3. For 7, it's 5 and 7, since 7 is the new highest prime. 5 and 7. 9 is not a prime, so we don't set it to 9. We continue at 5. Then we have 5 and 7. Then we have 5 and 11. We have 5, 11, and so on. And if you look at this array, let's say you had like a number 7, or let's say you had the number 9, and that would give us the case 1 here, where it's a multiple of 4 plus 1. So we want to find the largest prime that's also a multiple of 4 plus 1. Well, we already calculated that in our array, and that means it's 5. So that means that we use 5 as our value p here. So And then we can do the calculation. 9 minus 5 for 4 rounds is just 1 round. So that means that Farmer John will win after 1 round. And then, yeah, so we continue doing this calculation. And we know that there are at most 5 times 10 to the 6 primes, or the number of cows in each room is at most 5 times 10 to the 6. So that means we can just do this calculation for all of them, and it'll still likely run in time. So yeah, and we can do this calculation by just copying the previous array values, and if the number is like equal to is a prime and is multiple of 4 plus 1 or plus 3, then we can set the new array value. So let's go check out the C++ code for this. So here's my C++ code for this algorithm. So we start off in our main function here with this generating primes function. I use the sieve of Aristophanes algorithm, which essentially makes an array of the primes and then goes through all of them and sets it 0 if it can't possibly be a prime and 1 if it still is. You probably want to memorize at least some sort of prime checking algorithm for your USACO problems, because primes come up fairly often in USACO problems, so you'll want to remember some way of generating them. And this is my preferred way. I won't go over this in too much detail though. So after generating all our primes, we do our pre-calculation function. This is exactly what I just showed you with the array thing, except I use an array of size 4, which is probably unnecessarily, but it works. So I just loop through all the primes, or loop through all the numbers below the maximum number of cows. And for each one, I just copy over the previous values of the array. But if it's prime, I also set the new greatest prime. So this is exactly what I went over earlier. And once that's all done and pre-calculated, we do the actual test cases. So I just set up a loop here to call this a run case function. And in this function is where we do all our works. So first I read in our input, pretty simple. And then I have these two variables, Farmer John wins on and Farmer John loses on. Instead of storing just the overall round count of each victory or loss, I actually store exactly which room it wins on. So like if there are 5 rooms in the barn, then it starts with room 1, then 2, then 3, then 4, then 5. And then next round, the numbers will store 6, 7, 8, 9, 10 for each room, then 11, 12, 13, 14, 15 for the third round, etc. So that way we know kind of more discreetly exactly which room on which round the that Farmer John could win or lose on. At the end, we look at these two variables and compare to see which is less, because if Farmer John wins earlier than he loses, then that means that Farmer John wins. Otherwise, he loses earlier than he wins, so we print out Farmer Nodge. So then in this for loop, this is where we actually go through all the rooms. So we have our first case. These cases are different than what I went over, but they still have a lot of the same ideas. So we have our first case here, which simply checks if it's prime. This is kind of like an instant disqualifier, since we know that Farmer John will instantly win if we have a prime. So we set Farmer John wins on to I, and we didn't break because any room after this we know doesn't matter anymore. So case 2, this is a multiple of 4, so Nodge wins in this case. This is similar to our case 4 from what we wrote. So we check to see if it's multiple of 4 using the modulus function. And then we set the fj loses on variable. So we set this fj loses on variable by multiplying by the number of runes in the barn, because that means that every round we go through all n rooms. So that means we'll have gone through the rounds times the rooms, different rooms. So we get ai over 4, that's just the x over 4 thing. And then we add the I because it's in the ith room. So third case here is exactly like the case 3 from our reading, or from our writing. So in this case, it's not a multiple of 4, but it is a multiple of 2. So that means it's a multiple of 4 plus 2. And in this case, John wins after x over 4 rounds. So we check to see if it's multiple of 2, and then we set the Farmer John wins on variable in the exact same way as this. And finally, in the last case, this is basically the combination of cases 1 and 2, since they are so similar. So we use our pre-calculated array and just do a simple lookup to see what's the greatest prime that's less than or equal to AI. And we calculate our new number of cows after Farmer John makes his move with that greatest prime. And then we just divide by 4 to get the round count that John wins on. And then we set Farmer John wins on to that new number. Finally, once that's done, we can compare which round Farmer John wins on and then print out the winner. So yeah, that's the general idea of this algorithm. You can see that its runtime is actually fairly quick. Actually, the bulk of the runtime comes from generating all the primes. Since this is an O of P, it's like log of P or something algorithm. And since P is very large, it could be up to 5 times 10 to the 6. So that's where the most of the runtime comes from. Just because our normal algorithm for running is so quick, we only have to go through every room once. So this is an ON algorithm. Thankfully, we only have to do this calculation once per test case, so that isn't that slow. And this solution does indeed run in time. So yeah, thank you for watching.